Okay, so for those, I will repeat because some people are right now. For those who doesn't have a Universidad Autónoma de Madrid account, you need to log in on this PC with my account, okay, which is this one. Because we need to install Visual Molecular Dynamics, and you don't have permission to do that. Okay? So log in with my account, and then Google Visual Molecular Dynamics, and download the program and install the program. Okay?
We will introduce the practical, okay? And this is the web page where you will have the hands-on and what we are going to look at together for this session, okay? So if you could just look at here and I will give the introduction. Okay.
I am sending the link to the my email.
Ah, perfect. My handwriting is not that good. Okay, so we are going to check QMMM system, and I don't know if you know this, it's about DNA. So one who knows a lot about that, I guess. It's a G quadruplex. So we will take a PDB, a protein data file, and you already have the structure. You have a vector file that contains everything normally you need to have for the practical, okay? So we want to look at the formation of the guanine radical cation. And we want to see if we have QMMM, so you have the scheme here, and we have seen this QM part and the MM of environment, and then the water. So we will check the system, and question are typically what is the size of the QM, how we are going to describe. What we want to do here is to see if we have here a hotspot where the radical cation that we can enforce to be in a certain place by constraint DFT, where it could go, where here the purple guanine. So we want to have an idea what is going to be the trajectory in a sense of the outcome of this one, because it may depend where it is. So this is the scheme of the 4 guanine that are making a square, and inside you have like a metal. Actually, it's not really a metal, it's a K plus that you will see in the simulation. You pile up 4 of them, and so you have this structure, they will be looking together, okay? So here we have a faulty guy, and the question is to which guanine there will be a coupling way. We can estimate this coupling either static point of view or in dynamics. Okay, so the first part is to do it only with DFT, constraint DFT, and then progressively we try to see, we won't go to the end, I guess, but what is the mechanism? Is this I go directly from the donor to the acceptor, or do I have some hopping that I want to sample in the structure? Okay, so this, we want to do that because actually when you have this thing biologically, you form atoxo-G, which is a major hotspot for oxidative DNA lesion. So the very first, I won't show it too much because then I give a bit of the answer, but you can follow this link that Andrew just sent to you. The first question is just to estimate the ionization potential for 2 guanine that are pi stacked, and in the practical that I will look with you, I give you already the input and you can have a look to the output directly. Sorry, I'm just trying. Nothing is so wrong. It's just because when it's Zoom, I have a little big. I just want to show them this one, and for now, I was having trouble to find it. Like I want to project this one, and I don't know how to find it. It's just there because my screen is a bit too reduced.
But if you share all the desktop, maybe.
Yeah, you're right. So this is the system we are looking at. And the first question is just to look at constraint DFT, and this is the input you can have a look at. It's the directory, so you need to charge the TGZ file, the TGZ file. Untar it, and we can have a look together. You have one input for the neutral guanine, charge 0, multiplicity 1, and the same one, charge 1, multiplicity 2. And we have a first estimate of what is the ionization potential for this system. Well, it's quite small, but you can see here we have a bit of a constraint on it, which are in the constant. So I chose the one that the input is relatively straightforward. I'm trying to put it now. So just to make sure all files are in this one and we look at them together. Okay. Sandro, I'm not sure I can share my whole screen. It seems it's not working. No. Don't know why. I will just stay on one for now. No, I don't know. It might be my configuration. Does anyone have the range of idea of energy for this reaction without looking the experimental data or checking the calculations in EV? we should be around, I don't know, like normally 7, 8 in gas phase, okay? And now after we play in the full system. So you have two subdirectory when you enter this one, and we are working with Dumont for now. So everything is for now is just a QM. So we are interested in getting this value for both systems and seeing if we are in the range of 7, 8 to use it as a reference for the QMMM. Okay. So this is the input we are looking at. And here we want to avoid over the localization of the bistack radical cation. That's why we enforce the charge to be on one value, but not the other one. So we impose that because of constraint reality. And otherwise, nothing too special. Just the basis set is just like big, but we have auxiliary basis set, so we don't pay for the price too much. And then we constrain some of the atom in the other system that you have here. So this is the gas, and then same thing with the environment here. But we will check later for now. Can you all see this set of memory directory on this file or not? No? So it should be in output, just Dumont 2K for now, and then gas CDFT, okay? So the way I gather things for you is that in part 1 and 2, we will be in Dumont 2K, where the name of the structure we look at, and after we go for GROMACS and its QMMM interface. So now we look at the gas phase system, and after we put the environment. Sorry, blue is not very big for you. No, this is gas and gas hot and gas. Okay.
Increase the font size.
Increase the font size?
Yeah,
I can try, yeah, sure.
If it's the font here.
Yes, that's my fear indeed, yeah. I didn't know the size, it's so broad. Yeah. Yeah, possibly. No. Preference. Yes. Does it make a big difference or not as much? No, I need to increase again.
I think if you press Command plus, maybe it increases the font.
Ah,
Okay.
thank you.
Not sure.
Yes.
Thank you. Yes, I would do. So in this slide, you have all the bases, the auxiliaries, some potential, but we are looking only the output. You have it for your own sake after, okay? So this is just a regular DFT. And then you can compare to the one where we put the DFT. Can you tell me if you have access to this directory now? Yes. So now we can have, I can let you grab the energy, but it's total energy, like, and you can have a look, but it's just pure DFT calculation. One is DFT, one is constrained DFT, and see if you can estimate the ionization potential. And there is a link that is given on the online to situate the experimental value that I just give you here, close to 8 electrons. Okay, 8 electrons. So we can see here, we will always be using for now PBE 50. And the total energy you can just grab if you want, because otherwise it's just a DFT calculation you know how to do. Okay.
This one is the one that is froze, right? Not the other.
The project of the code we will later. So here the config of the code we just enforce the top will be on the one when and then on the okay. So once you have the Q value for the gas and you subtract them, you multiply by 27.21, something like that, get the value in EV that should be in that range. And then there would be our first QMMM calculation. What you could do if you have a bit of time is to open this structure here, where BMD, if it's possible, if you have it. Did you all look at a PDB before? Some of you know all of you. So here is the structure with the PDB that corresponds to a G quadruplex. I could suggest you open whatever VMD or another one that you prefer. You see the input, we can spend a bit of time on it. It's rather short here. So we give a chart, the multiplicity for the QM part, the basis set, the auxiliary basis set to speed up a bit the process. We give the PVE 50% of exact exchange is to add for the chart transfer reaction. We know we like to work with high percentage of exact exchange. When we set up the constraint DFT here, and we define the donor and the acceptor, and the point is to make the bridge between the two here. Topology, some grid, some distribution, which is always nice for a biological system. Then the force field is just FN99. Then we give the list of the QM atom, and the number refers to the PDB. We can check together that. So it's a small QM part here, just the two guanine. And we put some keyword here for the counter anion and the water. And this is going to give us this output, which is quite big, a bit bigger than the usual DFT one, because we have a static environment now. And you see it's going to list every atom QM. So it's I'm in G3, G4 environment CDFT. So the input here is going to be QM, and then with all the link atom that you can see here. And then everything is just going to be the part for the rest of the system. This is possible because we provide actually a topology for that. And we also have we recover here a total energy, and there is the SCF energy and the energy, and then we have the summation of the two that we will take into account. Okay? And you will see it's very different from the one for the gas system, and we have this difference of the environment here. As I'm projecting, it's huge. I guess on your screen, it's a little narrower. Okay. So what we are interested is just here looking the output and checking this difference of energy between neutral, the radical cation, and the neutral. If you want, sorry, my screen is not adjusted, but you could also do that to get the final energy of everyone, just making sure to take the last one, and that will give you the area we look at. So looking at the energy, this is what I found. You should be able to find the same because we have the same output, okay? So here, when taking this total energy that I show you, the first one is the QM on this system in gas phase. The other one is the one for the system of the quadruplex with all the environment, with electrostatic embedding. And you see that you have a big stabilization. You should be able to find the same number as me, as I was using exactly the same one, okay? Which is going to be a big difference we will comment on later. So is it okay are you following or catching up? There are different output files, 4 of them, they go 2 by 2. We want to make the difference to estimate the ionization potential compared to the reference system, for which the method, the QM method we are using is 7.5. Normally vertical value is around that. If you check here, 8.2, but adiabatic 7.8, so we are not bad at all. And then we compare and we see that the difference between experimental and QM is actually rather small compared to the big environment effect we want to look at. Once I let you convince yourself these are the right numbers, okay, grabbing the file, I will just show, we can have a look to the structure together where I will show you how to use VMD just to make sure I'm following this number of the guanine that we gave. So this is a small piece of DNA. And here we are looking at some guanine. There are 12 in total, okay? So the problem is that here, just go. So you should be able, if you type the right number of the residue with index, to see that we are looking at this 2-1 that pi stack in the environment. So in the model gas, it's strictly parallel, and we apply a constraint on nitrogen to keep it pi stack, otherwise it would just have a distance not realistic. And now in this structure, I remove the water so that we can see, but there is water in the structure. We are looking at what could be the value of the radical cation placed on one of them with this one in the QM part, and all the rest for now is to be NM. In the next part, we are going to, let's say, activate all the guanine of the system. They could be transferred to adenine, but the coupling is bad, so we just look at this 12 guanine, and it's already a little challenging. Can you open BMD to see the structure?
What's the name of this file? Because I opened another PDB.
All the PDB should give you pretty much the same one. Okay. It's just I'm trying to project also what I use as VMD representation. Can you see it? Okay. So ever you have the one that has a bit of a different name, it's exactly the same. This one is the trajectory we look after, but it should be the same. So this is what I typed to get this. So this one for now I hide because we are not looking at it. I am truly sorry because on my screen I don't see it. The fact it's big for me, it's a big of a drawback. Okay, so if you open it, you can just ask to draw res ID here. 3 and 4. We are looking at guanine 3, 4. So we are selecting this one not because we have experimental proof that it's the most stable place to put the charge. It's just to try a first computational part and set up, and after we are going to activate the other guanine. So before you launch, you look at the structure, and after from the structure, it's done here for you, but you are able to give this number here to provide the QMMM calculation, okay? It's not shared, sorry. Yeah, each time I have to know to do this trick, so. Okay. Could you please tell me if some of you managed to assign this value? Yeah, to find them and to be able, no?
You need to remove the representation from one. Not one, no, it's only resident one. Although the families are the rights. Is what. So if you put not resident what. So we can play with those selections and selection. But it's really useful.
So normal here. And just do that. You don't need to actually put the number of the atom. You could also just like give residue 3, 4, 5, 3, 4, 20. 20 is going to be for later. So for now, I can just forget about it. And here I see the 2 guanine, including the sugar and the phosphate, okay? And they are pi stacked. And they are pi stacked because this is what affords the best coupling. If we try the hydrogen bond one, the coupling is much lower. So by default, it's going to be lines all, so you can change here in drawing methods to try to have something a bit less big to see, okay? So new ribbon here. And then here, the residue you want, and sometimes I'm using that just to see the phosphate a bit more. Is it more clear? I apologize for that. Okay. So now we can all look the structure together. Okay. Is it more? I let you the comment here. What we could do also, actually, Igor will also use VMD. So you know, you will learn a little bit. It can do quite a lot of things. So if I do that normally, and I'm sorry because my screen is not what I'm used to. It's a bit disturbed. But if I do that, it's not very precise. If I do res9 GG, and I have to do that to make sure. Now we can check the structure, and you should be able to see in licorice, which is the thicker mode, the 4 stack of guanine, which should be 12 of them. Can you see them on your screen as well? And actually, if we want to have a look, we can just specify another one. And I think if we do his name K, we can make sure we put the counter anion, but otherwise the structure is going to collapse. So you see here, I can just like put them in green if I want to. They are here just in the middle, and they are charges, so they could play a role because perhaps it's not as good to have a positive guanine close to a counter anion that is positive too. So I'm just going to have this one. So the question could be, what could be the QM part we want to look at? And if we assume we want to do charge transfer between all the guanine that have the same HOMO, basically, then I will have the 12 of them, but then it's a big, we'll do it later. And then we begin for now just to look at 2 of them. So I can remove that to see them a bit more clearly. Is that more clear? Yeah? And now we are going to do the QMM partition. So it's done automatically. And what is going to happen is that I'm going to give the numbers for all the atoms here and all the one down. And that was done for you in the input file already. Okay. So if I change just there, here is the QM part. And now the frontier is going to be the nitrogen carbon bond. Okay. So going back here to what we are aiming to do. So this is the input file that we have seen. There are some constraints on the nitrogen to just avoid that it deviates. So it's to mimic the mechanical embedding of the quadruplex and enforce the planarity and not deviate too much from the stacking. We have this so for the neutral compound, and then you have it also for the radical cation, and doing the difference of the two gives you an estimate that is not too far from this value here, close to 7. Okay, so this is in gas, and then we do it as it says here for this PDB structure. So you have a structure that molecular dynamics with water and counter anion, and then we select what we want here as a part. And now you have question like, how is the part described with the force field? And you have a summary of ET module that we are going to check together. ET stands for here, like electron transfer or charge transfer. And you have a QM only energy that you can find also and compare directly. If you want, what we could do is to discuss the QMMM, and after I look together with you at DMD for those of you not familiar, or at project, and we can have a look together. Okay? So here we have done this calibration, so it's really a calibration of what could be the effect of QMMM, and we see that the effect is like 2.2 dB, which corresponds to a solvation, but also to the fact that charges are heterogeneous. So what we would like to do once we have get an idea of what is this big effect that is lower than the one that corresponds to the choice of the DFT or stuff like that, we are going to go to QMMMD and we are going to plot some energy over time. Okay, so here I'm changing directory, so you will go to the subdirectory called Romax, and in this one you are going to have specific files that are made for you that we will discuss that correspond to describing a guanine. And to do that, I will tell you a word about that. We are going just to look at one fragment orbital with DFTB. And this I will just like let you have a look. You should be able to find in the directory guanine.spec, which is to specify guanine as a fragment. We can look together. Charge transfer from that is to parameterize the charge transfer. If once you are in this directory, we can have a look together. I will just. So we leave a bit Dumont 2K for now. And in GROMAX, you have only one directory, and this one has a PDB, a topology file, and some files that, can you tell me if you see them, average file and TB Hamiltonian, okay? And the big output file, actually, we can have a look together, but it's not going to be as helpful here because everything is going to be stored in the file that we can plot together. I'm just going to change here. Could you just tell me if we are all this set of files? Okay, so the PDB file, it's the same one we just looked together, okay? So if we want to do the QM calculation, we are going to have different auxiliary files that are guanine.spec, which we can have a look at, and then charge transfer, and then a PDB for the structure. One is the trajectory and so we start from this one, and then we have the one that is going, there are two files, sol and no sol. And then we have the trajectory, which is the big one that we can have a look, but it's a dull trajectory where not so many things happen because it's stable here. So we want to describe guanine, but this time we want to describe all the guanine together. So in DFTD, one thing we can do is to just say how is going to be described the guanine. So this is my QM part. So I'm going to say 16 atoms, 56 electrons, one QMM bond. I could put two, but there is no need for that here. And then I'm going to say where I'm going to redistribute charges on this atom with specific name. I will show them where they are. It's just one step further the NDI positive bond. How many fragments? I would use one. And then there are other parameter that is a correction that is more useful if you have metals here. So we have here 28 fragment orbital. It's just 56 divided by 2 here. It's a closed shell system. So this is how we are going to describe the guanine, specifying the number of QMMM bonds and how to redistribute the charge and also the amount of charge to be redistributed. This is what I described this morning. and we split over 2 between these two ones here. Is it okay for the definition of that file? Yeah. Now we want to do a charge transfer. So once I have a guanine, I could just add another one if I want to. So we need to have this file, but a parameter in the bromates that are going to give us the integral we need for. And then we are going to transfer a whole here, which is my positive charge. And we have some scaling factor, some correction here. And I'm going to have 12 2M parts. And each of them is going to be controlled by guanine. So it's really one fragment, and I have 12 of them. And then I'm going to give the number of the guanine. So if you take the PDB, you could check that if you ask where is ID, it's going to be exactly all the number here of the guanine. And all of them are going to be of type 1 because I don't do another fragment, which would be another part, another promoter, another nucleobasis. I'm going to do DFTB2, which is this site SC, and I'm going to use ref for describing the charges. So here, the main important thing is the number of QM zones here, and I'm going to describe between them.
You generate automatically the rest charges.
The rest, yes, everything is done, redistributing, like it's going to be done along the dynamics automatically. Yeah. So we can have a look a bit at the output, but it's a very big one, so it will be easier if you check on your screen, okay? It's going to tell me I'm going to do a DFTB2 parameter, molecular dynamics here. And then that's the input that I just showed you. And then it's going to bring all the orbitals with some things. What is interesting, I will show you on the PowerPoint a bit later. Like this are the 12 one. I do not shift everything. Shifting if you have different energy to try to favor the interaction. One first thing that is done here is to set up the difference of charge onto the two atoms that we have been selecting for the 12 one. And then written down here all this equation. So here it's you only have the energy and the coupling. We are not going to have much more information than that. It's going to give us all the coordinates in the PDB and just give us what is happening. I'm just going to change. So we can have a look at what is going to give us this file here. Just increasing a little. It's just could you please launch this command to have it on the big screen, and then I will just for that. So what we are going to do now, we have this system and we are going to have the dynamics going on, and we are just going to take the variation of the energy of the HOMO, that is Boltzmann theorem, the variation of ionization energy. And all the terms here are electronic coupling because it's symmetry. You are going to have them in the coarse-grained Hamiltonian, that is TB underscore Hamiltonian. This is the equation DFTB we are going to use, and then we want to have an idea of the distribution of the charges here. The way it works, there is a tough communication between the QM and the MM part to be able actually to go from this positive charge going on to this one. As you can see, it goes through that. There are some fragment orbital, and you are going to do it a little bit step by step to take into account the electrostatic response. So we have this matrix that is going to describe the interaction that is going to be the TB Hamiltonian one. We can plot it, and how does it look? At first, it was a bit surprising. We are going to have a bunch of lines here at 0, which are the coupling, and they are very small compared to the ionization potential. Here, the ionization potential for the 12 guanine, they are statistical. So this is a 1 microsecond trajectory. And there are not so many variations. We could have just talked a little before, okay, but this is not a very heavy calculation. So here I can draw the running average, and I can see that there is one, well, you can believe me, you can also just plot it. There is one that seems to be a little below, and all the range, I have all this fluctuation that I would not have if I just taking one structure. So the idea here is really to have something QMMM over a long time and to be able to see there is one guanine that is the lowest one. So I will show you with X and Y how to detect this one, and it does correspond actually to the one of D20. And then we are going to look why this one will be a little bit different. So I go back to X and Grace. Were you able to plot this one from the TB Hamiltonian? So normally now you can play a little bit to try to detect. You can do the running average because on such long trajectory it's going to be a bit more visual. This is how I make the yellow one appear. And I will do it with you just to convince yourself that this is the 20. So the way it's stored in the Hamiltonian, it goes like that. So this is going to be number 1, then the interaction with 2, 3 up to 12. Then I go to number 13, and then 14 is going to be the cross interaction between guanine 2, guanine 3. So in the end, if you do the math, you should have 77 lines in the TB Hamiltonian. So ever we look it together to keep in mind that it's a trajectory, but we can also have a file that is called average if you want to go faster, but it's the average over time of this value here. For now, we look only here, and then we check a bit the coupling. And during that time, I suggest that you identify. So for me, on average, line 58 corresponds to guanine 20 because of this triangular matrix that I showed you. And you can have a look at it with DMD, type in raising ID 20 and try to see why this one would have or not a lower ionization potential. So you have this one, and you also have after, we will switch off the environment to see what is going to happen. Can you tell me if everyone is looking at this Hamiltonian, TB Hamiltonian? Yeah. So for now, we look at the site energy. In part 3B, we are going to look at the coupling. The coupling, as some of you certainly know, is underestimated by DFTB quite strongly. before we look together to the different one, could you tell me what could make, like, change the ionization potential of the guanine in the biosystem? So here is the trajectory, just to show you, it rotates, but there are not so much fluctuation. This is a stable, even at the microsecond, like rotation, but overall there is no unfolding event or whatever that we would have seen the coupling. So for instance, if I check this structure, what could change the affinity of the guanine would be the presence of the counter anion, possibly. But they are all symmetric here. I will just draw all of them to make sure of that. Okay. So it's a 3 piles of 4 guanine. So piling up 3 quartets of guanine. And in between here, the counter anion that actually does not move so much. So what could change is the exposure of solvent. But normally they are quite symmetric, apart one of them.
The 20 is not exposed, is that right?
Also, a tiny bit, we could compute the solvation of it, yes, to see. So they could have different mobility, but actually in this structure, it was not the case. So can everyone reproduce the structure where VMZ that is over here? Yeah. So the 21 possibility to explain that is that if you draw it, but you have to draw it the wall. You see here, you have a part of the phosphate, and it's making a nitrogen bond with this one that is stable over time. So I can just go. Zoom is really interfering, so I'm just going to plot that bond and see it. Between these things, so I'm going to so yeah, I will remove this one because it does not help. If you check the guanine and you try to see the phosphate, the interpretation we can have is that this 20 is close to the phosphate that is negative. So possibly there is a stabilization effect by electrostatic effect. Okay. And to check that, if you go again to this directory of bromax, you have TB Hamiltonian, and there is one that is called no sol. Do you see it? Can you tell me? You could just plot it x and grace minus nxy, TB Hamiltonian, minus x1 with TB Hamiltonian no sol, and you will see what happens between sol and no sol. You can do a difference of topology, which is suggested in the online written. Okay. So we want to see if the guanine would be different by turning off the electrostatic to comfort this interpretation here. Okay, so from here you have another 5 TB Hamiltonian, no sol, XVG, that you can also plot using the same one, X, you know it twice, you take 4 arguments, and it's going to give you another set of data that correspond to what is called no sol, and you can have an idea of what it's doing by doing a diff command between the two topology. Could you tell me when you do a difference of topology, if you see what is difference between the two one? Is it okay? Like you all plot here just the same command, but minus nxy TB Hamiltonian no sol. How is the Can you tell me like what is going if we do it, it's too big, verify the topology. So it's better to use this command to see really. So what has been changing here? So actually here it's like the point charge that you should know for water, like the delta plus, delta one, delta minus, they have been changed to 0. So it's a weird way to create some effect. We are just like making all the water not electrostatic anymore. Okay, just to see what it gives us. And here you see a bunch of ionization potential. You see the big effect that it has, but then when you do that, is it realistic or not? Actually, just a way to see what is happening and to create an effect. But doing this, we keep the sodium, the counter-anion, the phosphate, so it should not just have not so much of a meaning, just a way to try to do in gas phase light, and then things change a lot. This is what we want to do, okay? And then the scale is a bit different. Some coupling are negative. Actually, the coupling here, they are underestimated compared to CDFT. And we add this effect here. So one way to just turn off the electrostatic here, if we do on DNA, we have not integral charges, so it's a little bit harder, but it's just to say this, all this charge that I show you in the electrostatic embedding, we switch for the solvent to 0 because it's easy to do. And then we see that the structure actually really doesn't want that much to make the radical cation here. And we have a value that are not so much meaningful. So now if we look at this structure, normally when you are plotting here according to the ionization potential and rescaling, you have one hotspot that could be the one that is triggering and giving in time more stable interaction because there is a phosphate nearby. And we would not have been able to have it if we were just looking at the whole structure and we'd add that to dynamics. You could also see that if you try to do the same thing with 5 steps, there is a coupling. You have all the coupling value. You can take an example. If it's hydrogen bond, there is no coupling. It's almost 0. The corresponding, like for instance, in the TB Hamiltonian, 5 steps are the value that is higher, and hydrogen bond actually not so much, which is what we would expect in terms of orbital overlap. I'm just going to take time to check the MD web you sometimes just to make sure we can see the different going, okay? And I let you go through the exercise and ask me questions. Okay.
No, it's not. The only science and Nicholas.
So you can see the one
So, I'm told that it's because of the hydrogen bomb. We believe it's because of no, but here you are not more exposed to solvents.
There is also the contribution of solvent that played a role, but we found that the post-its hydrogen bond is stronger than stronger one, but they might be
more exposed to people that makes me wonder it's a little bit different when
Yes.
Just wanted to check with you. So in the average, you're going to have so the set corresponds to different couple of guanine. So you see there are some of them where the high value. This is the ionization potential. So it's the diagonal term of the covalent and Newtonian. And so this one has the inner grade ionization potential of 5.1. You have a standard deviation, and then goes a series of coupling. And then on 13, I'm going to have the second guanine, okay, which then you have this value, and then we have to remember it's a triangular matrix, okay? And then you can see the coupling. Some of them are really negligible, some of them are low, but they are probably underestimated because we don't have the full description of the DFT. So after what we can do is switch back to CDFT. Actually here, we have done one fragment per guanine. If we want to have more coupling, we can just describe 4 guanine in 1 QM part, and then have 3 for QM part, and it's not the same as 12 separated ones. They will communicate it more. And you have 77 because in that set we have 20. So if you do 12 times 12 minus the fact it's a diagonal, we count on this term, and you already have things here. And you can discuss in the practical the question answer based on this analysis. And the term that I was saying is, I think, probably this one is the lowest one, is just below 5, which singles out compared to the other value that are typically 5.3. So we are looking at an EV effect, difference of EV. So if you check the minimal value around all these 7 ones, I can tell you it's going to be this one, I think, which is B20 if you do the math. Okay. Okay. So, and then here we can see that compared to this one, there is still an effect which we saw at XM drive, the stabilization of that guanine. And the reason is not so trivial, indeed. There are mixed a bit of the effect as always in a heterogeneous system. Now, if you compare, this is the same one where we cut some of the electrostatic effect, and by plotting, we realize it's actually fairly different. And then we go back to the interpretation, trying to see what could be the effect that is playing here. So when you are in some grace here, just I guess you know that, but you can just do the running average to try to see a little more, because for sets to see one appearing a little bit more than the other one, okay? To detect that, because the fluctuations are still quite big on the system, even if I chose the one that is rigid. I think now, even the beginning was a bit hectic and I'm still struggling each time I'm changing. I'm trying to give you a taste, and which I think we still have covered quite of some questions that I wanted to show you today a little bit, like plot the time evolution. We compare the value and we try to see which guanine is favored, because now we have QMMM, we are able to describe a charged guanine, which is actually a trajectory. And then we have a trajectory behavior, which we saw a little bit. We have to compare with the environment. It was just to give you a critical example that you can see a lot, but it's not super realistic. I agree with that. So charge transfer, what do we expect? We expect G20 to be special. We don't know, I mean, I had the question, why this one? It's a bit hard to say, but the effect is here. And then the electronic coupling, we have to be a little bit more careful here. There is the question, compare the value here, like what would you expect as a value to say it's coupled? You can check that the pi stack are coupled, but not the hydrogen bond. And there is no full phase coupling between two guanines that could be too far, okay? This is what we could discuss now. Once you are getting out, looking at the file a little bit to get a place of that. Okay. So actually, this radical cation guanine, they were identified by time resolved spectroscopy. This is the link to a review. And we don't know where they are so much, but they can characterize. But then after, once you have the structure, you could do QMMM to generate some spectra and see if you have some signature, especially with G quadruplex for circular dichroism, for instance, to try to mimic the spectra, and it works quite well. This question we address also. The best conformation is to be pi stack, which we chose as a QM model system in the beginning, probably the share of the orbital. So for the time by West, you can try to assign perhaps different, like take on VMD to guanine, try to find the coupling value and see if it corresponds to your intuition or not. So experimentally, they can measure the time that this species is going to be stable before it reacts usually with water to form 8-oxoguanine, and the time range can be changed by several orders of magnitude. So there should be some effect to be captured by QMM. So to go back in time, we have seen how to do this DFTB-MM, or it's done by one fragment just to simplify the QM part and reduce it to one orbital to have describe the charge transfer. I should insist that we benefit from a very careful parameterization apart from the coupling, but the IP is extremely normally very good by the group of Elsner. We have seen a little bit of the QM part look like. The output is huge, so I just grab something here. Like this is the frontier. It has name special called QMM and MML, which correspond to the carbon nitrogen we are breaking. This is my QM part for this CQMs. And then here you have classical atom type. And then in the program, this one is going to be reassigned to the classical one. I don't need to define parameter. It's the one of the usual guanine. The charge are going to be different and done by red here. And then we go for this scheme to describe the dynamics, okay? And what we want is to describe the hopping process step by step, and this goes through the fragment orbital, and then I'm going to change progressively, activating the charges, and we're doing some atomic charge calculations that are hidden, and so you have a very compact structure that allow you to discriminate between these two situations. In the practical, also the tutorials, for instance, if you consider the distance, normally you decrease exponentially. So if you try to look at these two guanine here, you will not see no effect. Okay, this is the 10⁻⁹ that you have sometimes. And we chose an example where we have one guanine that is particular. There are several effects going on, so I don't know exactly why this one, but we are fairly confident here. Just to say a word of what can be done now with this kind of method, because for guanine, we could do also DFT or DFT on the fly, okay? So here is some nucleosome. So here it's really a big system. There are 64 guanine in the system. And what we are going to do is exactly the same dynamics. The difference is that you have some histone tail that are positively charged, and here you have all the phosphates, so they come and they are very disordered. They come to wrap the phosphate, but they are disordered, so you don't have them so much experimentally. It has to be done with careful, like calibrated phosphate to describe the intrinsic disorder, like EDP phosphate, and then we can try to simulate to get some confirmation. to run them for quite some time because, of course, this is going to answer when it's positive, lot of lysine mortality. When we have guanine here, we are going to have some interaction that should discourage the guanine to take the oxidation. Here is a plot, so an average over 20 trajectory, which you don't have in your practical line. We stay on guanine. So here what we have done is to try to see which histone, so it's a core of 8 protein and they have tails, so this maintains it's very positively charged here, and then here you have stacking interaction, you do a bit of 2 loop of DNA, so it's really a big system, even for classical already all atoms, but even for QMMM, but because the method is light, we can try to see which guanine is taking the oxidation. And here we have been plotting as the ionization energy from 4.2 to 5.4. So the point was to see as it compared to a G-quad or BDNA, what is the effect on environment. So here we saw that G20 was 4.9 something. On a big system like that, it's very heterogeneous from the electrostatic point of view. We can go even to 4.4. Okay, so we can have this big range of system, and then now we are trying to decipher, is it because there are some protein interaction with the tail that disfavor, or because there is some guanine that are more inside than other one more outside, or is there some other kind of interaction, like if I have a stack here of 5 guanine, it does not exist. Actually, it's more 4 of them is the maximum. Perhaps I have some coupling between them. But just to give you a taste that we can run such dynamics even for longer time and at the micro scale at the QMMM level. And to give an example that is published, and it's not from, like for another group, what you can have a look, and it's very interesting from a biological point of view, is if you have DNA and you have an abasic site, so you make a hole in the DNA, so this is DC, parallel with some alternation, but they are just nuclear bases. Here, X stands for abasic site, so I'm putting a hole in the structure, so I know I'm going to have some change in the property and the charges is not going to transfer so easily. Ever I put it on one strand or the other one, and it's slightly different. And then using parametrize, so Indo is semi-empirical with MMMD and then Monte Carlo to get the whole transfer, because Monte Carlo is going to be very good for that. They are able even to propose free energy for different structure and see what is the effect. So black is undamaged reference DNA. GX is when I am going to put the defect on that side, and the other one, GX prime here, and try to see what is the difference. You see the free energy does exist in EV, and try to see what is the sequence effect and why, and proposing structure to see how it readjusts when I'm doing this. So another example here of the whole transfer that is relying also on semi-empirical QMMM.
Which program they use for the like big systems?
Yeah, it's they have their own made program, okay, I think. But normally all the Monte Carlo, I think it was written, they give it upon request if you want, okay? So perhaps it's a recent paper, okay? So normally, yeah, you can have that. And for now, I'm just going to let this and answer some questions. And if you can just check the output and ask me questions just to try to get a feeling of the program is running, okay?
So it's everything more or less what we wanted.
Sorry, it's like each time I have to change the screen and it's
Yeah, so no, I apologize for that because it's not comfortable for you.
you just I don't know why my screen does not readjust or
But
Yeah.
For the end of the tutorial, one thing we could do is just to go back a bit to Dumont 2K and check the output because there are many information which are hidden in the DFTB code of GROMACS because it's driven by your MD software. So they just want to give a bit of electronic, but you don't have a lot of details. But here, so I was going to, let me check, to output 1403D, Dumont 2K, G3, G4 environment with constrained DFT. And then we can just like, go together of the calculation. You also have some spin density information. We can have a look at the charge, which is influenced by the environment. We could compare the charge of the waving QMMM of the guanine compared to the charge for the system that is the reference one. And everything is done at the same level, of course. Okay. So we can have an idea how the environment is changing the charges of the guanine here, okay? So here, just the input. All the list of the which, so when it's driven by the, so this is a QM code that is doing the QMMM, and GROMACS is more like they use DFTB, but more hidden in a more hidden way, okay? So here I'm going to have, if you want to look at the spin density, for instance, or everything is written with capital letter and just check the energy and so on, okay? Convergence is fairly rapid because it's a really quite a small system and we had to define a donor and an acceptor here. You could also see what could be the effect of not using constrained DFT, run the two guanine with no constraint, and you will have over delocalization and an over stabilization because of that. Okay.
So it's going to change much the conformation.
So ever like if you have this constraint, it's not going to change much, but if you change the conformation, I think the guanine are not so normally they are just an angle of 36, 30 between them, 36. And it's going to make them a bit more aligned, which is not the case in this structure so much. So here, a bit of spin combination that we can cancel. Here goes also all the different terms of the energy, including the one that we described together this morning, like for instance, the Lennard-Jones, QMMM, everything is just printed out, which is not always the case in the code, and the reason why I chose this one here. So if you grab energy for input.out, you will have all the one that are coming into, and you could even, like checking on this one, convince yourself, like, is it additive or subtractive calculation? We also have here the impact, initial adiabatic, final adiabatic, and an idea of the gap vertically. And another thing here I could have mentioned before is that really the MM is going to be a perturbation of the QM that plays a role and change, but it's not like the other way around, okay? Because there is all the compensation for the charge here. So normally the QM is going to drive here the total energy. You could just actually do the calculation with QMM energy and only with QM to see what is the effect, and you will find these two ET that I mentioned in the beginning.
The unit for display from
So this is normally the energy I was using. I can put the PowerPoint to estimate the ionization potential. And then in the GLOMAX code, it's going to be done automatically for you because there is not per se such a precise calculation. QMM calculation on the fly would be too expensive. So here this is which create Yeah. It's just like they are with output, so when you have them, it does not have so much products from the way we
Okay, so you are done.
Yeah.
Perfect.
Okay, so